Okay, let's get going. Good afternoon, everyone. My name is David Barry, geostatistician in the Perth office of Geovariances, and today's webinar is titled How to Properly Prepare Your Data for Rigorous Mineral Resource Estimation. This will be about a half-hour-long webinar. You'll all be muted, but there is a questions section in the GoToWebinar interface, and you'll be able to type any questions you have during or at the end of the webinar into that interface. Hopefully you're all able to hear me. If someone could try the questions interface just to verify to me that this is all working, that'll be appreciated. You'll get a copy of the webinar by video link in about 24 hours. I don't know the precise time, but certainly within a day or two. So this webinar is about data preparation. So fundamental concept of GIGO, garbage in, garbage out. One concept we can think of is if we have a cost on a vertical axis and data accuracy and quantity on a horizontal axis. Sorry, my mouse has become unresponsive, not a good start. There we go. So we've got two curves and then a sum of the curves in a total cost at the top. So in the blue dots, we've got the cost of collecting and preparing data. And if we put no effort whatsoever into data collection and preparation, then we don't have to spend much money on it, but we'll have a large cost in the form of modeling errors. And as we increase the amount of work we put into the data preparation, then we increase the cost of that and we reduce the cost due to modeling errors. And the context for this webinar is that you've basically already done a lot of drilling in a mining project. So we've incurred quite a fixed cost of collecting the data, and now we just want to put in a few preparatory steps to make sure that we're working with reliable data sets before we go ahead and start doing geostatistics. So we'll be starting with QA/QC data. So the geologists in attendance will be more closely familiar with this part of the process than I am. I've always relied on that work, making sure that the assay measurements have been well done, and you do duplicate analysis on your samples and so forth, make sure that the database is reliable. And at the end of it, we'll be ready to move on to some sort of estimation or simulation process, like kriging or something more advanced. And before we get there, before we start doing variogram modeling, we want to check and that the data is appropriate for that sort of work. And there'll be a number of steps that sometimes necessary, sometimes optional, that would go into that stage of a project. So the first thing is basic data analysis, visual checks on the data before you do anything with it. The next one is titled sample clustering. We might think of this more generally as domaining, separating our data into hopefully stationary domains. So regions of the deposit that show similar statistics. Now, this might have already been done for us. The geologists may have drawn some wireframes for us and said, yeah, this is the mineralized regions and so forth. Or there might be a whole series of different lithotypes that have been coded into the data set when it gets imported. And in those cases, the amount of work in the software is quite minimal. We just have to turn those geological codes or wireframes into something that can be used to limit each calculation to one domain at a time. If that work has not been done and we need to figure out what the domains are ourselves inside Isatis.neo, then we do have a sample clustering tool based on a machine learning algorithm, geostatistical hierarchical clustering, that with a bit of iterative work could be used to generate those sorts of domain codes. We need to look for duplicates in our data at some point in the procedure and the overall process. If you have two samples that are located at exactly the same coordinates and you end up going to kriging, you will get an error. It's not allowed to have two samples at the same location. The kriging equations can't be solved. So in some sense, you could argue that it's maybe not super important to do this step, because if it turns out to be necessary, you will find out about it when you get to kriging, because you'll just get an error. So maybe for the for a smoother overall process, it is actually important to do this step at the beginning and avoid any errors later on, rather than going through a whole lot of work and then realizing that you have to go back and tidy things up and maybe do a few things again. Compositing. So if the imported assay measurements are on have different sample lengths, then we'd have some sort of theoretical problems in working with the statistics of those data points, because the statistics of the grade when averaged over a 50 centimeter interval would be very different from the statistics of the grade when averaged over a 5 meter interval. And so if you're putting all of those different samples, grades on different lengths into some sort of statistical analysis, it's not really clear what we're doing. And similarly at the estimation stage, so when you're running a kriged estimate, it wouldn't make sense to give equal weighting to a sample that's very short and a sample that's on a much larger interval. So it's usually required to do a compositing step to composite the assay data into regular intervals, so that we have at least approximately a data set that has samples of the same support size, support being the geostats term for the volume on which something is defined. All the grades being defined on the same interval lengths, plus or minus some tolerance. We may also need to do declustering. What this is it's a correction of the bias that can be introduced due to preferential sampling. So the usual case is that you drill more densely where the grade is higher, and that makes sense because that's the most economically valuable part of the deposit. You want to really understand what's going on there. You don't really care so much about the lower grade areas. But when it's all part of one domain, a domain might contain some relatively higher grade areas and some lower grade areas, and the higher grade zones might be drilled more densely. Having disproportionately many drill holes in the higher grade zones would bias the raw statistics upwards. It would make it look like the overall mean across the entire domain is higher than it really is. And so it can be useful to correct that bias for various reasons. If you're doing the more advanced topics involving Gaussian transforms, so simulations, for example, or uniform conditioning, then I would say this step is extremely critical. the bias in the raw statistics would feed directly into the simulation results. And you'd be reproducing the bias in your output. For kriging, it's not quite as important because kriging will automatically decluster in doing its estimates. Nevertheless, there are some arguments which, to be fair, they go both ways on the importance of applying the declustering weights in calculating the variogram. So I'll be showing that shortly when we move into the software. And also something that we might do is capping, so applying a top cut to the variable because the raw values might be very large, and sort of pseudo outlier values make it more difficult to interpret a variogram. The variogram being the sort of the central tool of geostats is calculated by squaring differences of sample values. And when you have a very large value in your data set, it would be very different from the other values. And when you take squares of those large differences, the square of a large number is a much larger number, and that makes the interpretation of the statistics very, very difficult. So we might apply a top cut to limit the influence of those a relatively small number of high values on the variography. Now, you don't necessarily need to do all of these steps in all projects. It will depend on your data. But usually you'd have to do some or most. And now it's time for me to jump into the software. So here I have an empty looking Isatis.neo window, but this does actually have some data loaded. So for purposes of the webinar, I've got this file here, drill holes before QC. So something is strange about this data set because we haven't fully done the QC on it yet. So I just dragged my iron variable into this 3D viewer area, and something that immediately shows up is that I have lots of drill holes down here, and that all makes sense. But the extent of this goes a long way north. If I sort of view from the top, looks like I have some drill holes up at about y equals 10,000 instead of 1,000, so maybe some sort of database entry error. And I could zoom in, I can click on these drill holes, and I can see there's drill hole line 179 and 177. And in a real project, I could then go back to the database and say, okay, is there something wrong with those entries, probably in the collar table of the database? Something I could also do, could load the tops, the collars table as a label, and then I have the line numbers shown as part of the 3D scene. If I look elsewhere, I might also query this hole that seems to be running sideways. That might be an error in the survey table with a wrong dip. And it appears as though I have two overlapping drill holes here. So that could also be an error. Maybe genuine twin holes, but that would also be something to look into. And so these are sort of simple visual checks that you can do, just making sure that the data looks like it's supposed to before you start blindly calculating statistics on them. So, for example, with the with these two drill holes here, I might query if there's, or try to figure it, okay, in one sense I can click on these and say, okay, it's line 42 and line 43. So I can do that visually, but what I could also do, I could use the look for duplicates task. I'm on my tops table here, and I could ask for collar locations that are within, and here I put 5 meters, and I've got some outputs, and I press run, and it tells me that there's a number of mask samples, 1, which means that it's found a group of, it looks like 2, which corresponds to those 2 drill holes that are right next to each other, and it's removed 1 of them that I could then sort of keep removed from the rest of the process. And I've done this calculation here on the collars, but in general, you might need to do this on the composites table if you're running into the problems of, or potentially running into the problems of kriging, having duplicate samples in the kriging neighborhood, 2 samples at the same location. In those contexts, it'll be referring to the composites rather than the tops. And so you'd load a composites file and run the same sort of analysis. And the result of that calculation is some variables on that data table, which you could then sort of study in a variable editor. So, there's something, lines 42 and 43, that's what we saw in the 3D viewer, but now it's been found in a more sort of programmatic and repeatable way. So you could have this as part of a regular workflow to ensure that the databases of drill holes has been imported and is behaving as you expect. So now I'll pretend that I have gone back to the database and fixed all of those problems and switched to this file called drill holes, which doesn't have any of these issues. And I'll talk about domains. So there's this lithological code variable in this data table, and this is the tutorial data set that comes with the software. This has been done for us. So we imagine the geologist has coded each of these samples according to some lithotypes. If I make a histogram, say, let's go an upper bound of 20, see that they take distinct values, 1, 3, 6, and so on. And what's the meaning of those lithological codes? Well, I can go to statistics by category and set my categories to the lithological code, and iron is my main variable. And I run this, and I've got my different categories in the first column here, and I have my iron statistics in the main part of the table. So by looking at the mean column, I can see that I've got very high grade iron in these first 3 domains, 1, 3, and 6, and lower grades in the next 2, sort of intermediate on 12 and 13, low in 15, and 99 is probably some kind of placeholder, not really classified samples, which we might ignore. So in many contexts, this sort of domain coding that's been done before you import, that might be where you end. You say, okay, those are the domains I want to use, and we could convert that into a categorical variable, because at the moment when I imported it, it just told it, yeah, they're just numbers. I just used the default settings. So there are some parts of this software, notably in the compositing task, where if you have a domain variable, you have to describe it as a categorical variable. This sort of tells it what sort of variable this is. It's not just a regular numerical variable like the iron grades. It has a special meaning. So that would be sufficient for many circumstances. In this case, for this tutorial, we could simplify the analysis. Rather than doing the statistics on all of these different domains, we could say, well, let's just group the high-grade domains together, and we'll group the low-grade domains together, and we'll ignore 99 as unclassified. And so in those cases, rather than having a simple right-click and convert option, I'd go to Data Management, Create Categories from Rules, and I would define rules for what my final domains are based on the values of that lithological code variable. So I have my assay table loaded. I've got my lithological code as a numerical variable, and I've created two rules. It's going to be rich ore will be the 1, 3, and 6. So I'll just simplify that to being less than 10. And poor ore is going to be 10. And I've set up to less than 99, so not including 99. And I'll create a new categorical variable called domains. In the tutorial, it's called final lithology. They're the same thing. So that's how you would work with domains that have already been coded for you. The other possibility, if that work hasn't been done and you've just got a whole heap of grades and you think, okay, I need to make domains out of this somehow, the tool we have is in the statistics menu. It's called sample clustering. Create a domain variable. And the inputs to this calculation are some number of grade variables, some number of categorical variables. Here I've put iron, and I've actually taken the log of alumina. Just when you get these distributions that look like this with long tails, I find that the taking a log transform does a little bit better in this hierarchical clustering tool. We also give some weight to the coordinates. I've put a very low weight to start with, and I ask it to calculate, and it generates 3 different domains here in green, orange, and blue. And from the box plots across the bottom, the ones of interest are the 2 on the right. We've got iron on the horizontal axis and the log alumina. And we can see that the clustering tool has separated out a very high-grade iron and low-grade alumina, a somewhat high-grade iron, and a very low-grade iron. And you see the low-grade is more at the periphery of the domain. The green ones are away from the central area, which is mostly blue and orange. And so maybe you could say, well, the blue and the orange seem to intermingle in the middle of this domain, so, or in the middle of that ore body. So maybe you could group domains 1 and 2 together and treat domain 3 as a waste. Or maybe you go back and you try iterating, what if I change the weighting on the different variables? And you can go back and forth, try to come up with something that makes geological sense and also seems to divide the data set into different categories in a meaningful way. So that would be the alternative procedure for creating a new domain variable. But I will use the existing one, the final lithology or domains. And the next step would be compositing. Most of the things I'm doing today are in the data management tab of the ribbon. Most of what I'm doing is sort of pre the statistical analysis, which would be in the stats menu. But it's always a bit of an iterative process. Sometimes you jump into the statistics and see what's going on inside the proposed domains, and sometimes you go back to data management and so on. Compositing, we composite our drill holes. We have a selection on which drill holes or which samples in the drill holes we want to composite. The domain support here has to be a categorical variable. So our choices are the the lithological code cat, which contains a different domain name for each different lithological code value, or the grouped one, which I call domains, or could be called final lithology in the tutorial. The composites that this tool creates will never cross a domain boundary. So that's the use of this domain variable here, is it ensures that my rich ore samples will not be composited together with the poor ore samples. So I should probably go back and demonstrate that I've selected the 5 grade variables for compositing. On the next step, I choose the compositing length. I've got a histogram of the lengths here, and maybe if I edit the axes, oops, max of, let's say, 15. Looks like most of my samples are less than 5 meters, and maybe 5 meters would be an appropriate compositing length. We've got various options on what to do with the residuals, so it'll try to make equal 5 meter composites down each drill hole, but if you've got a couple of meters left over, that's called a residual. You've got various options on what you want to do with that little bit left over at the end. And it might not be at the end of the drill hole, it might be at the end of a interval of consecutive domains. So the rich ore, when it flips to a poor ore, that's a domain boundary. You might have only a couple of meters of left in that domain before you hit a boundary. That's also a residual for these purposes. So there's various options there, simple ones and more advanced ones, depending on how long the residual is. I'll just leave it at merge residual. On the next page, we have a statistics table of our different domains and all of the variables that are being composited, raw, composites, and residuals. And so the check that we'd be doing here is that the mean values are behaving in a consistent way. We don't expect the compositing procedure to change the overall mean in a systematic way. It may happen sometimes. You may get a systematic bias in the lengths of the samples, like you might assay the high grade areas at a more fine resolution. But usually you expect similar numbers here, no change to the mean as you go to the from raw to composite. Each of the domains presents those statistics, and I could click finish and generate a new table. The one that was done in the tutorial is actually a 15 meter compositing length. So basically, once you've done the compositing, all of the subsequent work is going to be done on the composites table. This is where our final set of grades are, and that's where we'll do our variograms and anything else. So one thing we might do is declustering. Here I've switched to the map view, so I'm looking at the color locations in a 2D map, and I can see that there are certainly areas where there's more dense drilling and some where it's more sparse. And with a ruler, I can look at where it's more sparse. It's 250 meters between those two drill holes and about 200 there, 200 there. So something 200 plus or minus some amount would be the regular sort of drill pattern where it's not clustered. So if I go to data management declustering, here I've brought up Illumina. I could say known window size, let's do 200 by 200 by 15. And this will move a box of this size over each sample, count how many samples are in it, and weight each sample, or weight that sample by the inverse of that number. So if there are more other samples nearby, that sample will get down weighted in all the subsequent statistics calculations. you can make a graph of the results of, here's the mean value of the alumina as the moving window size goes from 15 by 15 by 15, which is extremely small, to 300 by 300 by 15, which would be probably too large. And we can see there's actually a bit of a little transition around about the 200 meter, 200 by 200 window size. So you could create that weight variable, declustering weight for alumina, and in subsequent statistical work, you could apply that weight variable. So in a simple case, if I open the, oh, I should probably do alumina for the alumina weights. There's a weight option here. Oops, should be declustering weights. And so with the declustering weights applied, I have this mean of 2.00, and if I remove it, 2.13. So I am getting different results with the weighted statistics. And the last thing I might do is variable capping. So if let's remove some of these. Here I've got alumina. Let's go on the full data set just to really make this look horrible. Very difficult to interpret this variogram. Like it's very irregular looking. And if I look at the histogram, we have a long tail of high values, and variograms are very sensitive to these sorts of high values. So, you know, if I get rid of them, the shape of my variogram changes quite substantially. But it's a little bit aggressive to entirely remove samples from a calculation and never see them again. So we might prefer to just cap the values at some level. And the variable capping tool, which is in the statistics menu, helps guide us on this process. We have a table of possible cutoffs and their percentiles, the resulting mean after capping, and we've got a standard deviation, coefficient of variation, and the metal loss. So metal loss being the percentage reduction in the mean after you apply the cap. On the right, we have some graphs. Here I've got the coefficient of variation. And maybe you might follow a rule of thumb that says you want the CV to be less than about 1.5. So I think 1.5, all right, let's try this one. Shows me that the cap is here. We could also look at the NP plot. Some people would interpret a big gap in the NP plot as indicating where there's been some break in the distribution and we should apply a cap there, and then maybe that would be back down here. There's no objectively correct answer. This might be capping, you know, this would be more than 5% of the data being capped. Maybe that's too much. As it turns out in this case, part of the problem is that I've lumped all of my domains together. If I use my rich ore selection, now I look at my coefficients of variation and they're all less than 1. If I look at my raw histogram, there's really only one sample out here that could be argued to be causing any problems. And if I go to the poor ore domain, there's really no outliers to speak of at all. So the domaining turned out in this little tutorial baby case to be the solution to the problem. But in other scenarios, you might want to use this tool, create a new variable for your capped grade, and then use that for your variography and subsequent estimation. So that's the lightning tour of sort of data preparation steps that you might go through inside Isatis.neo. And let me see if I can go back to the presentation. So you've got some time to type some questions into the questions area. And while you're thinking about what questions you might ask, some words about geovariances. We offer consulting services to help you implement the techniques shown in this webinar and others. Geovariances, now part of Vela Software, Datamine, global provider of geostatistics-based solutions, market leader and reference. We've had a technical partnership with the Center of Geostats at the Paris School of Mines since mid-1980s. So a lot of experience in the company in geostatistics and software development. We have 40 plus technical experts, consultants, and software developers. The head office of Geovariances is in Fontainebleau in France, very close to the School of Mines. I'm in the Perth office, and you can see that this slide has been made by a French person, as I'm in Australia. We also have offices in Brazil, Chile, and a new one in Toronto. We have some upcoming training on mineral resource estimation, recoverable resource estimation. Check details, websites for, these are on the European time zone. We also have training courses run for the Asia Pacific. URL there, or contact one of us. We can provide the details on the training courses being offered. And we offer consulting services, performing and auditing resource estimations or building estimation routines. Something that may be of interest is the CFSG. This is a French initialism that means something in translation like higher learning or higher training cycle in geostatistics. This slide is based on the European version of this course, which people are able to do, but there'd be some pretty late night lectures for the Asia Pacific time zone. There will be an option for a CFSG condensed course, I believe in November, for people in the Asia Pacific time zones, if there's sufficient interest. So if you want an intensive course in geostatistics from people in the School of Mines and also the with practical projects run from Geovariances, then get in touch with one of us, and we'll be happy to see you as part of the course. And so now we get on to any questions that you have, and I look at my questions dashboard, and we have one from Mark Krejci. It's how do you do K&A, which maybe not quite the main focus of the webinar, but because that would be a little bit later in the procedure. So what I've talked about so far today has been all the preparation work that you do before you start your main statistical analysis. The next step would be going to EDA, and then you load your maybe a capped variable, or you choose your domain and your weighting variable, and you model a variogram and so forth. And once you save that in Isatis.neo to a geostatistical set, we've got some saved with the tutorial data set here. You go to kriging. Let's load a variogram model. Choose our output block kriging 5x5x1. And here is where you get to start choosing how you want to do your K&A. There is a button here that allows you to do K&A usually on one slice of a grid. Like if let's just change this to like 124 just to get something going. So you can, yeah, so either on the whole file or on one slice of the grid. And if you use this tool, you can vary different neighborhood parameters, so the orientation of the ellipsoid, the size of the ellipsoid, number of sectors or number of angular sectors, etc., number of samples, and generate some graphs. That way you get a big table of the results. That's one way of working. The other way, which is my personally preferred way, is you go to the end of the kriging procedure. You actually do the whole kriging run, context K&A, and I can look at these output results and say, well, my kriging efficiency here has a mean of 0.6, my slope is 0.9, some positive weights, that's 111%. That means I've got 11% negative weights. I'm not happy with having so many negative weights. So I go back and I saw maybe instead of 24, I'll do 16 samples. And no, it's still too many. And you can iterate your way to a neighborhood in that way. So there's a couple of different ways that you might do K&A. Alan Troncoso asks, the idea of capping is to use it to fit the variogram, but then you do the cross-validation with the original data, or do you continue with it for the workflow? There's a couple of different possibilities here. One is that you cap and then that's it. You're going to work with the capped variable for the rest of the procedure. And you'll be aware that probably you'll be underestimating the grade in some areas because you know there's really more metal there than you've put into your input variable. There is a technique, Rivera and Durem, I think, wrote the paper on it, where you split the modeling into a couple of different steps. You first cap the variable, but you also create an indicator variable for telling you if a sample is being capped or not. You co-Krieg the grade and the indicator, and then you spread the sort of extra metal that you expect over the resulting estimates according to the Krieged indicator. Now, just me saying that out loud, if you're not familiar with the procedure, it may not make any sense. But I guess the take-home message would be that there is a technique that exists to try to do both capping so that you get a more robust variogram being calculated, and also in a way that you don't completely lose that metal at the estimation stage. In terms of cross-validation, I suppose I would, my gut reaction is that I would leave the capped variable in for cross-validation, just because if I'm capping the variable, I expect that those really high values are very different from the rest of the distribution, and I wouldn't really expect them to help in reproducing estimates of nearby values. I think they're very different. So my personal take, at least as an instant reaction, is that I would use capped variables in cross-validation, but I would have to give the enormous caveat to that remark, which is that I don't do that very often. I could imagine people having a different opinion, but mine is that I would use the capped value. And that's all the questions. When I close the webinar shortly, you'll be prompted to fill in an evaluation form. So we'd be happy to hear your feedback on the webinar and your potential future topics that you might like to suggest. So please do that. Otherwise, thank you very much for attending. You'll be given a video link sometime the next day or so if you want to watch a recording of it. And see you next time. Bye-bye.